And we have, oh man, I missed a definition. Dang it. Ah. Ugh. All right, so definition. C infinity P is set of functions smooth near P. All right. So here we have P is an element of a manifold M. All right. So then if we have X is a mapping from C infinity P to C infinity P such that number one, X of, let's say, CF plus G is Cx of F plus X of G, and 2, X of Fg is equal to XF, X of F, G plus F, X of G. I'm feeling guilty here because I am supposed to write the point dependence. So of P, I mean, sometimes I slap a sub P on here just because it just feels right. Because this is all being done at the point P. So what I'm saying here altogether, guys, is that X sub P is a linear map on the functions at P, all right? And it satisfies this number 2, which is what? What's number 2 good for? The product rule, right? So this is the product rule. So this is sometimes called like the Leibniz or product rule. And XP is an element of what we call derivations at P. Derivations at P. But notice we've defined derivations algebraically, all right? So what I was just getting into over there is the fact that this proposition here shows you that if we have a constant function and we feed it to a derivation, right? If xp is a derivation, and we have, f is a constant function, right? Then xp of f is just equal to 0. All right? I'll go through the argument on the projector once I turn this thing off here. Oh, what's going on here? Ooh, that's not good. All right. So this is kind of sneaky. You have your constant function, all right? You've got your other function, just make it identically equal to 1. Then if you do that, f is equal to f times g. This is a kind of sneaky step, right? And so then you can do the Leibniz rule. xp of f is xp of fg, but by the product rule, it's this and that, right? But notice that f of p is equal to the constant, and g of p is equal to, well, 1. So we get this plus that, but then look, you've got both places. They cancel. It leaves you c times xpg is equal to 0, but then you can pull the constant inside, and once you pull the constant inside, you're back to f again, which shows you that xp of f is equal to 0, where f is a constant function. So we can derive a derivation acting on a constant function is 0 just from the algebraic properties, you see. But it is what it sounds like. A derivation is a derivative, all right? And the proof of that is actually somewhat involved. It's easy enough to prove that the partial derivatives that we've looked at already are a derivation, right? That was the properties we just looked at, wasn't it? Linearity and the product rule. So every partial derivative is a derivation. Is every derivation a partial derivative? That turns out is something a little bit more technical, but it turns out to be true. So let's see, this proposition 8.28 here, this says that if two functions are equal for all x near the point P, all right, then it follows that the derivative, well, the derivation at P acting on F is equal to the derivation acting at P on G, right? So, great. And this right here, we can define, this is kind of the big proposition, which says that if you have a derivation, you can rewrite it as a linear combination of the partial derivatives we just introduced. What that means, because we're going to be able to prove that these are linearly independent. So they're a linearly independent spanning set for the set of derivations. The partial derivatives with respect to the coordinates form a basis for the derivations, is what I'm telling you. The proof of this is not easy. You need this lemma that if you have a smooth function, then you can rewrite the formula for the function in terms of these GJQs like this. So this is kind of it's not exactly the tangent line expansion. It's like it's an analogous to the tangent line expansion, except instead of having constant, you've got functional coefficients, which we're using the GJ to denote. Again, I don't even have a proof of it in here. But if you have that, and it turns out this right here is where we need the manifold being smooth. This is actually not true if your manifold is like just k times differentiable. You can't do that in that way. You run up into the issue of being like twice differentiable but not 3 times differentiable, like it ruins this construction. It turns out that this set of derivations over a CK manifold is not, so what I'm telling you after the dust settles here is that the set of derivations is actually m-dimensional for an M manifold. And we're going to say that the set of derivations is the tangent space to the manifold once we have a little bit further discussion here. In contrast, if we were talking about CK manifolds, the tangent space, we couldn't identify the tangent space with the set of derivations because they're actually infinite dimensional. Like assuming smooth is what makes this work. So anyway, so you take the formula for f, you feed it into here, you let the derivation x act on it. This is a constant, so that's 0, about what we just talked about. This over here, now we've got a product rule, so we do the product. We've got xp acting on xj, gjq, and then this over here. But then that simplifies down to this because we're also assumed that xp of 0, which you can always do without loss of generality because you can always shift your coordinate system to make the point you're interested in become the 0 point for your coordinate chart, simply by just subtracting a constant off the formula that you have to start with. So we can always look at a coordinate chart assuming xp is being 0 when we're doing these kinds of derivations, which makes this 0, which just leaves us with this. And lo and behold, f being arbitrary, we've shown that the derivation xp is equal to xp of xj times partial xj. So then, the natural question to ask next is, okay, so we've got a derivation. We can either write it in terms of the x coordinates or we can write it in terms of the y coordinates if we have both, right? And so on the one hand, we'd have an x coordinate expansion. On the other hand, we'd have a y-coordinate expansion. How are they related? Well, we already talked about that. We know that we can rewrite partial y as in terms of a sum over partial x's. So we can plug that earlier result into here, this right here, and we plug that in, and that shows us how the coordinates, the components of the derivation xp relate from the x versus the y. That's what equation 8.2 is right here. This is how the y coordinates for x for the derivation relate to the x coordinates for the derivation. This is the coordinate change formula. This is analogous to like the formulas we were working at before break, where we had like the p and the p inverse, you know. This is like the p matrix is this thing now, basically. Our coordinate change matrix is now found by partial differentiation of the one coordinate system with respect to the other. Don't worry, we almost never actually do this. It's just something that we talk about. Like actually doing it would be a total drag. So in summary, the tangent space we're going to say is the set of derivations. And while we're doing all this, I should really talk to you a little bit more about why does this make sense geometrically? Like how are derivations related to tangent vectors geometrically? So this discussion I have right here is due to Barrett O'Neill, who has a phenomenal text called Elementary Differential Geometry. And he points out in that text that if we look at the directional derivative from Calc 3, even, right? dpf acting on v, right? The formula for that is v dot the gradient, right? Which is this, which is that, times that. So even there, if you go back and look at it, you could think of the vector v being associated with the derivation right here. Right, missing a c? Oh yeah, thank you. Helpful. Cool, yes, I shall add that. Bonus point. So, it could have been yours. Could have been yours.
There's also a typo in the homework.
Oh, you got to tell me about these things. Oh, the v being e? Yeah. So,
Is there it's an e?
mm-hmm.
Do we get credit for finding errors in the text?
If you find them before Violet.
Because earlier there was a definition in which you misspelled constant.
Well, you have to email me these things.
Okay.
Yeah. So so here's the deal. When a derivation xp, namely a partial x, b partial y, c partial z, at the point p, acts on a smooth function, what is it doing? It's describing the rate at change, which f changes in the abc direction. In other words, a derivation at p generates directional derivatives of functions at p. So this is what the partial derivative on the manifold is doing, is calculating the directional derivatives. It's the same thing as in Calc 3, really. But the new thing is we're going to take a weird step and say vectors are derivations. That's the weird new idea, right? Like, wait, what? Vectors are derivations? Yes, for us going forward, vectors are going to be derivations on smooth functions. That's how we define a vector in a manifold. Well, that's one of the ways. And so that brings us to the push forward, which I'd hoped to get to today, but you know what? I'm content with my life. So we'll stop here and not try to rush through the push forward, because it shouldn't be rushed through. I will push it forward to next class. So, sorry, I regret that.